Hi everyone, I'm Greg Stitt, and in this talk I'll be continuing our discussion of FPGA timing optimization by illustrating some of the most common optimization strategies. First, if you haven't watched the initial video that defines the necessary background, I highly recommend watching that before this presentation, but in any case I will start with a quick review of the important concepts. So timing optimization is the process of ensuring that for all paths between all flip-flops in a design, the summation of the cell delays and interconnect delays for each path is less than the clock period plus the clock skew minus the flip-flop setup time. Or if that is too confusing, just think of it as ensuring that the delay between flip-flops is less than the required deadline. Now, it's important to ensure that this condition is met along all paths in the design to avoid setup violations that would cause incorrect functionality. Now, hold violations are also a problem, but are less common, so they won't be the focus of this talk. One more important concept to remember is the setup slack, which is the difference between the deadline and the arrival time of the data at the destination flip-flop. In mathematical terms, the slack is the clock period plus the clock skew minus the setup time minus the delay between flip-flops, which is just the summation of the cell and interconnect delays of each path. When you compile an FPGA design, the timing analyzer will evaluate this setup slack for all the paths, and if any of the paths have a negative slack, that means you have timing violations that must be optimized. So, how do we do this? Well, keep in mind that once we decide on a required clock period, we only really have control over the delay between flip-flops, which leaves us with two optimization options. One, reducing cell delays, and two, reducing interconnect delays. So, the remainder of this presentation will go over the most common optimization techniques for each of these different possible bottlenecks. This is by no means an exhaustive list, but I will be presenting techniques that are sufficient for many situations. Before we get into the specific optimizations, first it is important to understand the overall methodology for timing optimization. So initially, you need to determine and specify timing constraints for your design, which I described in more detail in the previous presentation. But for now, just assume this specification means providing a constraint that requests a specific clock frequency. Second, you will compile your design in your synthesis tool, which as one of the final steps includes running the timing analyzer. Now, this timing analyzer reports a very detailed list of timing statistics for the design. One of the most important statistics is the total negative slack, or TNS. So this total negative slack is the summation of slack on all failing paths, or all paths essentially that have setup violations. So if this is positive, it basically means there are no timing violations, which is what you want. But in the more common case, it will be negative, and the magnitude of that negative number provides you with an estimate of the effort that will be required for timing optimization. For example, if the total negative slack is negative 0.01 nanoseconds, that will likely only require very small optimizations on one or maybe several paths. But on the other hand, if the total negative slack is less than negative 1,000 nanoseconds, there are going to be some huge timing bottlenecks in your design. So next, you will take the path with the worst negative slack, which is what we call the critical path normally, and use the timing analyzer to identify the sources of the timing bottlenecks along that path. Basically, we're going to analyze that path and look for cell and interconnect delays, or possibly both, that are causing problems. So after identifying those bottlenecks, you will then modify your code to apply one of the upcoming timing optimizations to eliminate that bottleneck. You then jump back to step 5 and repeat the analysis and optimization for other paths until there are no more failing paths in your design. However, one thing to be aware of is that you will occasionally want to jump back to step 2 and recompile the design before looking at other paths. The reason for this is that after performing some optimizations, the timing characteristics of the entire circuit may change significantly. So some of the previous bottlenecks may have gone away, and there could also be new bottlenecks that didn't exist before. There really isn't a formally defined methodology I'm aware of, but generally what I do is fix the obvious bottlenecks in the topmost failing paths and then restart from step 2. Another common variation of steps 4 and 5 is instead of just taking the path with the most negative slack, you can very frequently identify patterns in the failing paths. For example, you might see 200 failing paths that are the same path in different instances of one entity, but they aren't the critical path. But obviously there's a problem there that is occurring a significant number of times. So you might want to prioritize fixing that path because it occurs so many times over the actual critical path. That way you reduce the number of failing paths by a huge amount, which then makes it easier to focus on the remaining bottlenecks because there might just be a small amount now of failing paths to analyze. So now that we've seen the procedure for doing timing optimization and how to select a path to optimize, we then need to go about identifying bottlenecks along that path. And first, we're going to focus on bottlenecks caused by cell delays, which usually means logic delays, but it can also mean delays incurred by anything other than the reconfigurable interconnect. So for each failing path, the first thing we'll do is identify the types of cells along that path and the corresponding delay of each cell, which I'll demonstrate in a later video, but that information is provided to you by the timing analyzer tool. So these delays will primarily consist of lookup tables, embedded memory delays, and DSP unit delays, depending on your exact circuit. But based on the FPGA you're using, if you have different types of resources, those delays from those resources may play a part in this. Now, in the case that RAM delays and DSP delays are dominating the total delay of your critical path, or even if LET delays are dominating, your best first option for optimization is to consult the device-specific recommendations. This usually means digging through the datasheet and understanding low-level characteristics that can be used to reduce the corresponding delays. So exact strategies vary across FPGAs, but common examples include registering the output of embedded RAM resources, avoiding certain read during write behaviors in RAM resources that can add extra logic and slow down your clock, structuring multiply accumulate operations to more efficiently map onto DSP units that are in your FPGA, and in general, just writing code that ensures the inference of a specific FPGA primitive by the synthesis tool. So to find this information for Intel FPGAs, search their documentation for recommended HDL coding styles, and that will basically tell you how to write code that will infer a particular type of resource during synthesis. For many situations, the most common cell delay that you will run into will be caused by lookup tables, which is where we will spend most of our time talking about optimizations. These lookup table delays are caused by combinational logic, which gets divided by the synthesis tool into a hierarchy of lookup tables. So our goal is going to be to minimize the longest path through that hierarchy of lookup tables, which we will see examples of on the next few slides. All right, so when trying to optimize lookup table delays, our goal is to optimize the logic in our code to decrease the maximum lookup table hierarchy depth. To do this, it is critically important to realize how lookup tables implement combinational logic. So basically, the one rule you have to remember is that an n-input lookup table can implement any n-input, one-output logic function. So the number of inputs to your logic function is really the most important thing to consider, and the number of gates is irrelevant, which can be kind of counterintuitive, especially if you are used to ASIC design. So what this means is that any combinational logic function with more than n inputs is going to require more than one lookup table. Now, it is also common for lookup tables to have multiple outputs, but I won't be talking about the implications of that in these slides because optimizing the number of inputs is far more common. So the example at the bottom of the slide illustrates how the number of inputs to a logic function can affect the required number of lookup tables. Let's say that our original circuit is a 6-bit comparator, meaning that it has two inputs that we'll call A and B that are each 6 bits, and those get compared to produce a 1-bit output. And for this example, all of these inputs and the one output go through flip-flops. Let's also say that the FPGA we're targeting has 6 input lookup tables. So what this means is that the corresponding combinational logic for this comparator has a total of 12 inputs because we have the two inputs A and B, and those are 6 bits each. So we have 12 total bits. So what this means in the FPGA is that we're going to need more than one lookup table. So the synthesis tool is going to allocate one lookup table that compares the upper 3 bits of A and B, because that gives us a total of 6 inputs, which maps perfectly onto one of these lookup tables. Synthesis would then use another lookup table to compare the lower 3 bits of A and B, again, to give us a total of 6 inputs. And then the synthesis tool would use a third lookup table that compares the output of each of the previous 2 lookup tables to create the output of the comparator. So this implementation requires 3 total lookup tables for the combinational logic. But more importantly, for timing optimization, it creates a maximum cell delay through 2 lookup tables between the flip-flops, which could potentially cause a timing violation. So we want to see if we can reduce that maximum cell delay from 2 lookup tables down to 1 lookup table. So now we're going to take a look at the common strategies that you can use to reduce these lookup table delays. Now again, there are many more strategies than what I'll be talking about, but the ones I'm presenting are the most common ones that I run into. So strategy 1 is shown on this slide, which focuses on reducing the number of logic inputs, which should make sense now that we know how logic maps into lookup tables. By reducing the number of inputs to the logic, we can hopefully fit that logic into fewer lookup tables and hopefully reduce the depth of that lookup table hierarchy. Now, there's probably thousands of examples we could look at for how to reduce logic inputs, but I'm going to stick with this comparator example to keep things simple. So, one strategy we could have when you're using a comparator as part of some other circuit is to modify that circuit to try to place constants on as many of the inputs of the comparator as possible. Clearly, this isn't always possible, and it often tends to be highly application specific, but for this comparator example, one example use case where you could apply this optimization is for when the comparator is used alongside a counter. So let's say we have this counting circuit and it needs to count some number of times, where that number is specified as an input that gets stored into a register. So it's basically a non-constant input. And let's also say that both the input and the count itself are both 6 bits. Now, one very common way of implementing this circuit would be to count from 0 up to the number stored in this input register. But if you do it that way, you end up with the exact comparator we just saw on the previous slide, because if we look at this comparator now, it's comparing 2 inputs. It's comparing the count and the actual input register. Both of those are 6 bits, so we have a 12-bit logic function. We know that's not going to fit into one lookup table. So we want to see if we can optimize this further. Fortunately, we can do something that's a little counterintuitive, but works quite well. So in this example, if all we want to do is count some number of times, if we don't care if it's up or down, we just want to kind of wait for some number of cycles to elapse, we don't have to count from 0 to that number. We can count from that number down to 0. And if we do it that way, the comparator has now replaced the second input with a constant 0 because you are always comparing the count with a value of 0 instead of comparing the count to a value of a register. And by doing this, you reduce the total number of logic inputs to the comparator from 12 down to 6. And since we're using 6 input lookup tables, we can now implement this exact same functionality in a single lookup table, which reduces the depth of our lookup table hierarchy from 2 to 1. So this is a very effective optimization here. A second strategy for minimizing lookup table delays is to shrink the longest lookup table path using extra registers, which is generally referred to as pipelining. Now, this is probably the most useful timing optimization technique and the most common one you will be doing. So the basic idea of pipelining is to trade off an increase in latency for decreased logic delays in order to improve clock frequencies. And now, not every application is going to be able to tolerate an increase in latency. Many are largely insensitive to latency, and so for these types of applications, pipelining is very commonly used. So if we go back and look at this 12 input comparator example, there's going to be times where we can't reduce the number of inputs. So we are stuck with a lookup table hierarchy that is 2 lookup tables deep. However, what we can do is trade off extra cycles of latency for a significant decrease in lookup table delays by placing extra registers on the outputs of each one of these lookup tables, which is shown in the figure. So pipelining is a very powerful strategy. It will likely become your go-to strategy for most logic bottlenecks, but it does have some limitations to be aware of. So first of all, modifying latency by adding extra registers to a component can break the functionality of the rest of your circuit, which is why RTL synthesis tools can't do this for you automatically. So just be aware you might need to make modifications to the other parts of your circuit after pipelining one component, and those modifications could introduce new bottlenecks which require pipelining themselves. Second, and this is really more of a practical limitation, is that sometimes it can be kind of awkward to implement this pipelining in your code. For example, we have this purely combinational comparator that you can implement in RTL code using the equal operator. However, now that we want to add registers in the middle of that logic, we might have to design the comparator in a counterintuitive way where the code explicitly divides up the logic based on how it would be placed into lookup tables, and then put registers on the outputs of each one of those lookup tables. So this is clearly not a productive way of designing. Fortunately, there is a way of automating this in many cases, which we will see on the next slide. A third strategy for reducing lookup table delays is something called retiming, which is the process of moving registers either forwards or backwards to help balance logic delays. Basically, retiming tries to move logic from a stage with low slack into a stage with higher slack. The figure illustrates one example of this, where in the original circuit, we have 2 adders with no registers in between them, but with 2 registers on the output. Now, retiming can take the output register, shown in blue, and move it backwards onto both inputs of the second adder. This now reduces the maximum cell delay from 2 adders to 1 adder at the cost of 1 extra register. Or alternatively, we could have performed forward retiming and moved the 2 input registers on the top adder into a single register on that adder's output, which isn't shown in the figure. So in that case, we could actually improve cell delays and reduce register requirements by 1. Of course, we can't see what precedes the top registers in this example, so we don't actually know if that would be a good idea or not until we actually saw what came before this simple circuit. Now, retiming can be done manually in code by moving registers to exactly where you think they should be, or it can be done automatically by synthesis tools. But to do it automatically, you first need the registers to exist in your code. So RTL synthesis cannot change the timing of a design, meaning it can't add extra registers, it can't take away registers, it can only move around existing registers. So you have to make sure the registers exist. So automatic retiming is still very useful though, because you can use it when either you don't know where the registers should be, you don't know their best placement, or when you just have too many registers and it's impractical to figure out and retime them yourself. Or there's simple situations where it's just awkward to specify certain locations for the registers, like in the example we saw on the previous slide with the comparator. Automatic retiming can take care of that for you. Now, before you start thinking that automatic retiming can solve all of your timing problems, you need to be aware of some tool restrictions. Now, it's outside the scope of this talk to explain all the details of how to use retiming, but there are situations where manual retiming will do better than automatic retiming, and vice versa. So you can't simply add 1,000 registers on the output of your design and hope that automatic retiming is going to spread them out throughout your entire design in some optimal way. Another important issue to realize is that automatic retiming is restricted by the requirement to preserve the correctness of initial states of the code. This basically means that upon reset, there can be parts of the logic where there are slight differences between the original circuit and the retimed circuit. Now, those differences might be harmless. They might be there for just a single cycle and then disappear. But that is a problem for the synthesis tool because the synthesis tool doesn't know that they are not a problem. It has to preserve the same semantics as the original code. And so what this means is these initial states can often restrict the amount of optimization that a synthesis tool can do automatically. So in a lot of situations, you can run into these differences in initial states, and they may not actually affect the correctness of your design, but the synthesis tools have no way of knowing that. They're restricted by these initial states. And so if you know that those differences can't break your design, that is a situation where you will manually have to implement the retiming. So this slide here illustrates one of the big advantages of automatic retiming, which is that it can greatly simplify the code for pipeline designs, such as the comparator example we saw a few slides ago. So instead of having to explicitly write that comparator as 3 separate pieces of logic with flip-flops in between, we could have just simply added an extra flip-flop on the output and then enabled retiming in the synthesis tool, which would most likely have moved that extra flip-flop in between the lookup tables like we originally wanted it. Now, I've never thoroughly evaluated automatic retiming across different synthesis tools, so I can't give you exact guidelines on when to use automatic retiming versus manual retiming. So my suggestion is to evaluate it in a modular fashion to see if your specific synthesis tool will do what you want on individual pieces of your design before you waste time creating a huge design only to find out that you have to manually move around registers to do the retiming yourself. A fourth common strategy to reducing lookup table delays is to reduce precision. So for our previous comparator example, we could potentially have a situation where we are able to reduce our 2 6-bit inputs to 3 bits each. Now, the comparator uses 6 inputs total, which synthesis will map onto a single one of our 6 input lookup tables that we've been using. Of course, the obvious limitation here is that this reduced precision can't break your design. So this comparator example really isn't the best motivational example, since it would be rare to solely reduce the inputs to a comparator and still have your circuit function correctly. So this example really is just meant for explanation purposes. However, there are many realistic situations where you could reduce precision in other places in your design, which could in turn reduce the width of comparators and other logic. So machine learning and signal processing are widely known to perform well with reduced precision compared to other applications. For example, for some neural networks, 32-bit floating point is overkill, in which case the designer could potentially use 16-bit fixed point, or in many cases, even something smaller like 10-bit fixed point. Basically, the idea is to identify an application-specific reduced precision which then enables a ton of logic optimization that will also reduce lookup table delays. One important thing to understand is that reducing the precision does not guarantee a reduction in the number of lookup tables, or more importantly, in the maximum lookup table delay. One example of this would be if we considered a 4-bit comparator instead of a 3-bit comparator. So the 4-bit comparator would actually have the exact same maximum lookup table delay as the 6-bit comparator, despite the fact that the inputs use 2 fewer bits. So in this example, we don't actually see a reduction in delay until we reduce the number of bits from 6 all the way down to 3. So after optimizing all the cell delays on a given path, interconnect delays will then begin to dominate the total delay of that path. This is especially common for highly pipelined designs because that pipelining will often shrink the cell delays as much as possible. Now there can be many reasons for lengthy interconnect delays, but they usually result from a combination of 3 things. So one cause is distantly placed resources, which require long propagation delays across many of the FPGA's routing sources. To solve this problem, we need to find ways to place those resources closer together. A second and very common problem is high fanout, where a single source flip-flop may connect to numerous destination flip-flops. So the typical ways of optimizing fanout are either to reduce the fanout, assuming that's possible, to add cycles to pipeline the fanout, or to steal slack from other cycles. So that's something we saw with retiming, but with fanout, we're going to see it with something called register duplication. Finally, the third common cause of lengthy interconnect delays is congested routing resources. To optimize routing congestion, you generally need to reduce routing requirements by reducing the number of connected resources, which generally means you need to reduce resource utilization. So this slide illustrates the interconnect delay problem resulting from distantly placed resources. So how do we go about fixing this? Well, during the placement step of compilation, the placer actually tries to solve this for you by minimizing the distances of connections between resources, which it will almost always do better than a manual attempt at placement. So you usually can't shrink interconnect delays by improving the placement yourself. One reason why the placer can't always guarantee close placements is because of high resource utilization in your overall design. So the figure at the bottom illustrates a simple example of this problem. So let's say we have the simple circuit shown here, which is just a 4-to-1 mux with flip-flops on the inputs. Now, if we consider that Intel FPGAs lay out resources in a 2D grid of what's called ALMs, we can see an ideal placement in the middle of the slide where each input flip-flop is mapped onto a separate ALM simply because each ALM provides exactly one flip-flop for this example, and then the mux itself is mapped to a separate ALM because it has 6 inputs. So basically we're assuming here that the targeted FPGA provides ALMs that have a single 6-input lookup table and an optional flip-flop on the output, which is a pretty common ALM structure. So the reason this placement is ideal is that all of the connected components are as close together as possible on the FPGA, which will minimize interconnect delays. The problem is that when considering a design as a whole, it is often impossible to achieve such a placement because of high resource utilization. So the figure on the right shows an example of this where ALMs from other components, which are shown as X's here, interfere with the placement of the 4-to-1 mux, which then pushes the A0 input further away from the placement of the mux, which increases the interconnect delay after routing. A second cause for distant placements is the placer anticipating a large amount of routing congestion and spreading things out accordingly, which I'll come back to on a later slide. So for now, we're going to focus on this resource utilization problem. The first strategy for optimizing interconnect delays from distant placements is to reduce the amount of resources. Now, a comprehensive study of all the possible options is just not feasible here. It's application specific and it's well outside the scope of this talk, and it actually encompasses the entire area of digital design. So I'll just explain the basic idea of how this strategy helps with this particular bottleneck. First, one application-independent option is to try to change resource types to reduce the number of a particular resource that is causing the bottleneck. For example, delaying a signal by many cycles could use a huge number of flip-flop resources, but you could also implement that delay in any type of embedded memory. Similarly, DSPs on different FPGAs often have low-level optimizations that allow you to perform multiple operations within a single DSP. So if you modify your code to take advantage of these optimizations, you could potentially reduce DSP usage by a factor of 2 or more. Another general technique is to sacrifice performance, assuming this is possible within your constraints, by time multiplexing operations across fewer shared resources. The figure at the bottom illustrates how resource reduction can help placement take distant resources and move them closer together. So let's say, for example, we are able to optimize some portion of the design which eliminates the highlighted ALM. Now that that ALM is not used, the placer can potentially move the distant A0 flip-flop into this newly available ALM that is much closer to the mux. And in doing so, it has now shrunk the interconnect delays. Another strategy for reducing the distance between resources is to take a long routing path between a source and a sink and add extra flip-flops along that path. So this is another instance of pipelining, which we saw for logic delays earlier in these slides. So here, we're basically doing the same thing, but for interconnect delays, where we are sacrificing latency by adding extra registers to break up a long delay into several shorter pipeline stages. Pipelining wires like this can be a very effective technique, but it can also be awkward to implement. So first, you generally need to use the timing analyzer to identify distant connections that would benefit from pipelining in the first place. You then have to go and modify your code to add some flip-flops for the corresponding wire. The problem with this is that placement and routing aren't guaranteed to produce the same results on every run. So, a lengthy connection in one compilation might not be lengthy in another compile, and might be replaced by a different lengthy connection. It all depends on how the placer decides to place all the components in that particular run. So, you could add registers only to find that another path is now longer on the next compilation. So for a huge design, you could potentially iterate numerous times, adding registers to different wires with a bottleneck just shifting every time you compile. In addition, another potential challenge is that this pipelining increases flip-flop usage. In general, increased flip-flops tend to greatly help reduce delays, but above some threshold, some extra amount of registers can actually create new bottlenecks from increased routing congestion. Fortunately, these limitations don't always happen, so pipelining should be one of your primary strategies for reducing distant connections. However, for large designs, you do need to be very careful with how you choose the number of registers and where you put them to avoid these potential limitations. One more thing to be aware of is that the effectiveness of this strategy is highly dependent on the targeted FPGA. For example, Stratix 10 FPGAs have a pipelined interconnect called Hyperflex, in which case this optimization is very effective and likely avoids most of the potential limitations that I just talked about. So we just looked at how to optimize distant resources, and we're now going to take a look at how to optimize routing congestion. First, routing congestion occurs when too many signals or wires are routed in a certain area of the FPGA, which creates high contention for the routing tracks, switch boxes, and other reconfigurable interconnect resources. So the figures on the right show some examples of this, where the bright pink regions correspond to routing congestion. So the top example routes a large amount of signals through the center of this design, which creates a significant amount of congestion. Now the lower example has less congestion, which will be made possible through various optimizations. Now, the problem with routing congestion isn't the congestion itself. It is that when the router wants to route a signal through an already congested region, it must find an alternative, usually much longer path around that congestion. This longer path is the source of many of the problematic interconnect delays that we need to optimize. So again, there are way too many application-specific strategies to discuss here, but I have a few general ones listed. The first is one we saw before, which is to reduce resources as much as possible. With fewer resources, or fewer connections between resources, there is less to route and potentially less routing congestion. Another general strategy that we also saw before was to use time multiplexing, but in this case, we'd be using time multiplexed communication, or even something like a network on chip. So with this strategy, communication bandwidth may shrink compared to directly using the FPGA interconnect, but it also may have much simpler routing requirements. So as long as your application can tolerate this reduction in communication bandwidth, then this becomes an effective optimization for getting rid of routing congestion. Another potential solution is to use pipelining again, because you could pipeline the signals that get routed around the congestion, but we have the same limitations that we saw before. So a lengthy path in one compile that we pipeline might just get replaced by another lengthy path in another compile. So this pipelining strategy might just be shifting around the bottleneck on each compilation. Also, the addition of these extra flip-flop resources to an already congested design could potentially worsen the congestion and outweigh the pipelining benefits. Very often, routing congestion is caused by high fan-out signals, especially wide ones. So now we're going to spend a few slides talking about how to deal with that very common bottleneck. So I'll illustrate this in more detail in a future exercise, but the current recommendation is when analyzing interconnect delays in a timing analyzer, always look for nets that might have a high fan-out. This is a very common timing bottleneck, so it should be one of the first things you look for when trying to minimize interconnect delays. So one way we can optimize fan-out bottlenecks is through something called register duplication. First, the problem with fan-out is that it is often difficult to place numerous sinks for a high fan-out signal close to the source. So you end up with both distant resources and routing congestion. This is illustrated in the left figure, where the sinks of the fan-out, flip-flops 2 through 7, can't all be close to flip-flop 1, which is the source. One solution to this problem is to replicate the fan-out source register, which in this case is flip-flop 1. The right figure shows this replication, where there are now 2 copies of flip-flop 1, each having a reduced fan-out of 3 instead of 6, which allows for closer placement of some of the sinks. This improvement unfortunately doesn't come for free. In this example, we obviously pay a price of 1 additional flip-flop, but that's not the only cost. Register duplication also increases the fan-out of the signal that precedes the source register, in this case flip-flop 0. So if the path between flip-flop 0 and flip-flop 1 still meets timing constraints, then what we just did, this replication, is an effective optimization. However, in general, what register duplication is doing is stealing slack from the preceding path. So in this case, we're stealing from the flip-flop 0 to flip-flop 1 path to increase the slack between flip-flop 1 and all of the fan-out sinks. This means that in some situations, register duplication might just shift the timing violation from the original fan-out to some preceding path. In general, this issue makes it challenging to select the exact amount of duplication that is best for any situation. It can be done automatically by the synthesis tools, but in my experience, a manual exploration of potential replication amounts is usually needed, or at least can provide you with some benefit. One quick note about doing register duplication manually. Synthesis tools will, by default, synthesize away registers with the same functionality, which is what we have here with the duplicated registers. So the synthesis tool would basically get rid of all the duplications. So before you spend a bunch of time explicitly coding duplicated registers, make sure you look at how to disable this optimization in your synthesis tool. Or you can look at the Fanout code example on the repository where I will demonstrate how to do this for Quartus. A second strategy for dealing with Fanout is what I refer to as pipelined Fanout trees. The basic idea here is to handle a high Fanout signal across multiple cycles of lower Fanout. The figures on the slide illustrate this, where we go from the original circuit that has a Fanout of 8 from flip-flop 0 and convert that to the figure on the right, where we add a tree of flip-flops that uses 3 cycles to connect flip-flop 0 to all the sinks, but never exceeds a Fanout of 2. Like any pipelining strategy, pipelined Fanout trees increase flip-flop usage and latency, which has potential limitations that we discussed earlier. Another potential issue is that manual implementation can be awkward, especially since the optimal number of cycles and amount of Fanout from the added registers can be different for each Fanout instance. Fortunately, Quartus provides something called hierarchical proximity register chains to assist with automation of this process. Basically, this feature allows you to add registers before a Fanout source, and then Quartus will retime the design to automatically create the illustrated tree structures. One limitation of this register chain feature is that it places restrictions on your code that might require significant design changes, at which point a manual implementation might be more effective. To summarize everything we just discussed, I showed that timing optimization involves iterative analysis and optimization of cell or logic delays and interconnect delays. To deal with cell bottlenecks, we discussed a variety of logic optimizations, which are just a small subset of all the possible optimizations. Similarly, we looked at several common optimization strategies for dealing with interconnect bottlenecks. All right, that's it for this presentation. But now that we understand the potential bottlenecks and some basic strategies for eliminating those bottlenecks, in the next presentation, I'll be demonstrating these techniques in action by actually performing timing optimization of a simple code example. Thank you for watching.